Hello everyone, welcome to our differential equation class. In this video we are going to talk about graphical analysis of solutions to differential equations. We are going to start introducing the concept of the slope field of a differential equation, and then we are going to see that one consequence of understanding what that means is that we are going to find out that solutions of differential equations with different initial conditions, they never cross each other. Then we are going to introduce a new type of differential equations called autonomous equations, and for this particular type of differential equations we are going to introduce a way to find qualitative graph of the solution of the differential equation without actually having to compute the exact solution. So that's the plan for the video today. Let's start with the concept of a slope field of a differential equation. What is a slope field? Well, the slope field, or also called direction field, of a general first order differential equation, so here is the equation written in normal form. F is an arbitrary function, recall function of t and y. The slope field of that equation is a graph of the values of the right hand side of the equation, of the values of the function f on the ty plane, and these values are represented as slopes instead of points, as slopes of appropriately small segments. So that is the slope field. To understand a little bit better what do we mean by all that, let's recall the usual way we graph a function of two variables, t and y. The usual way to represent the values of a function of two variables on the plane ty, on the plane of variables t and y, is to represent the values of the function as points on a third axis. So we have here t, we have here y, and the values of the function at that point are represented on a vertical axis that we call f, and then at the different point different values and so on, so we end up with a surface for the values of f. So a little bit better picture is here. So on the plane here we have the plane ty. So here is the plane ty, and at any point on that plane, let's say at these values of the variables t and y, the values of the function f is represented along a perpendicular axis. Suppose a positive value here. At a different point we are going to have different values. At this point we are going to have a different values, and all the values of f are forming then a surface, some surface on R3. That's the usual way, isn't it? But here we are interested in a different representation of the values of the function f, because here we are interested in representing the values of the function f in a different way, because this function f is the right hand side in a differential equation, and the differential equation can be, we can attach a graphical meaning to this differential equation. To understand that graphical meaning, let's consider, for example, that we have one solution. Suppose this function y of t is some solution of the differential equation. We can graph this function, isn't it? So suppose we graph that function, we are going to get something like this. We are going to have the y-axis, we are going to have the horizontal axis, the axis t, and then the function is going to be some function here, that is going to be y of t. Some particular function. Okay, so now let's grab any point in the function, for example this point here with coordinates t and y. And what is the value? Recall, this is the value of the function at that point. So this is y at that t. At this particular t, this is the value we get. Okay, so at that point, what is the value of the derivative? So let's zoom up a little bit. Well, the derivative of this function at that point is the slope of the line tangent to the graph of the function at that point. So the value of the derivative is this slope. So what is the slope? Suppose that we have an interval here of 1 in the t variable. So suppose that right here we have t plus 1. So we have an increment of 1 in the independent variable. Then the length of this segment, when the horizontal segment is 1, the vertical segment is the value of the slope of that line. So this vertical segment is the value of the derivative of the function y. We know that from the physical meaning, the graphical meaning of the derivative. But now this function y, we said, is a solution of this differential equation. So that derivative has to be equal the value of f at that point. So the length of this segment, so that means the slope of this line, is actually the value of the function f. So having a differential equation then, what does it mean to have a differential equation? Well, one meaning of having a differential equation is that the right-hand side, so the differential equation, represents all possible slopes of all possible solutions, y of t, at all possible times. Because at every time and at the solution y, this is what we are giving, the slopes. So that is one way to interpret what is the information given in a differential equation. You are giving all possible slopes of all possible solutions. Can we, for example, see all that information at once? Well, one way to visualize all the information at once, all this information, is to graph all these points. And if we do it in the usual way, well, here are the points. But this is not very helpful because we are representing the values of this function. That is not good. The values of this function as points in a third axis. But it would be much more interesting for us, much more useful, if we could represent it as slopes instead of values on a different axis. So this segment is more important for us than the value of the function as a point. And look, this segment lives in a y-t plane. So if we want to represent this segment here, we are not going to do it here, we are going to do it down here. Actually, let's see, this segment has slope more or less of 1, because if this is 1, this is very close to 1 too also. So in this graph, what we should do is to plot, for example, this little line. Let's change it a little bit. Let's put it exactly what it should be. Should be more or less there, no? So that is a slope of 1, and this value of 1 here is actually can be represented by that slope. So if we have another value of the function here, for example, well, that value could be represented now by another slope somewhere down here. I don't know, it's close to 1 too, maybe another little segment there. And for each value of the function, we can represent that value as a slope, maybe horizontal if it is close to 0, or positive, or if it's negative, then as a negative slope, zero slope, positive slope. So here, zero slope, positive slope, or negative slope. But instead of representing the values of the function as points, we are going to represent them on this plane as slopes of small segments. So then we don't need this third axis, and instead we are going to do what is called the slope field, which is we are going to represent the values of the function as the slope of small segments, because this is what we are interested in this when the function f has the meaning of being the right hand side of a differential equation. So we only need this plane. So let's put this plane here. Now we have this little slope here. Oops, that was not right. We have a little slope here. Well, it's right there. And this is y prime, but now y, instead of y prime, what we're going to say is, well, if we have a solution, this is y prime, but right now this is f at the y. And then we can have the values of f at different points. So for example, at this point here, we are going to represent the value of f as a segment that maybe is a little bit more vertical, and here maybe more vertical. It depends on the equation. I'm just doing something to do something. Here maybe at this point the value of f is smaller than 1, so maybe something like this. Here maybe it's something like this, just to do something. And maybe here is something like this. And what is the value here? Well, I don't know, maybe something like this here. So depending on the equation, but at each point we can graph the values of f as slopes of small segment. How small is up to us. How many we want to graph, that determines how small they are going to be. So for example, maybe here we have more values of the slope, but you see that it's a very time-consuming work, because we need to plot each values of the function as little slopes, and that takes time and patience, and I don't have any of those. So that's why people use computer. People use computer to do that, because then you write the code and it's very easy to generate all these little slopes. But suppose we have something like that. Well, this is a slope field. When you graph the values of the function on several points on the plane yt, not as point, but as the slope of little segments. Here, well, this could be a possible slope field. And notice that now why this is more interesting for us than this picture for f. Recall here the only thing we have plotted is f of dy. There are no solutions of the differential equation. There is no differential equation. We are plotting a function of two variables on the plane of the two variables, instead of as a point, as we are plotting it as slope of segments. But if we do that, then any solution of the differential equation with this right hand side is going to be tangent to the slopes of the field segments. For example, if I put initial data here for the differential equation, then the solution has to be tangent to this little segment. So it cannot go like this. It has to go like this, because it has to be tangent. But if the solution passes through this point, it has to be tangent to this slope too. And if it passes through that point, it has to be tangent here, 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 here. So you see, having the slope field give you a pretty good idea of how the solution is going to behave. If the initial data is over here, then the solution has to be pretty much like this. Solutions cannot cross the slope field like here, because the solution has to be such that this slope field is tangent to the graph of the function because this function is solution of the differential equation and the derivative is this value of f. So here we have two possible solutions of the differential equation with different initial conditions. Here is with one initial condition, here is with a different initial condition. For any other initial condition, we are going to have different solutions. That was a wrong solution there. The solution cannot cross the slope field. So that's why this type of pictures is more interesting to us, because the function is actually the right hand side on a differential equation. More examples of slope fields. Now this is an arbitrary function f. Let's pick a function f. For example, let's pick the function f to be sine of y. So now this is f. And notice that it's not function of t, it's function only of y. Which means if we move on this axis, which is the t-axis, nothing changes because the function f that we picked here, sine of y, doesn't depend on t. So the slope field cannot change when we move on the t-axis. It's only going to change when we move in the y-axis. And we know that the sine of 0 is 0, so here at 0 the slope have to be horizontal. We know that the sine of pi over 2 is 1, so here all the slope have to be 1 at pi over 2. We know that at negative pi over 2 the slope is negative 1, so there's negative 1, and in between it has the values in between, but we need a computer to do it. But this is how a slope field for this equation would look like. What about if the equation depends on t explicitly on the right hand side? For example, we put this with a factor t. Well, then at t equals 0, everything is going to be 0, not because of the sign, but because this is 0 at t equals 0. But as we move in t, this value changes. So we start at 0, then it becomes negative because this value is negative. T is positive, sign is negative at negative pi over 2. So become negative, more negative, more negative, more negative, more negative, and more negative, and goes to vertical as we move to the right. If we put pi over 2 here, so 1, well, when t is 1, this is going to be 1, but between 0 and 1, this is going to grow from 0 to 1. And then for larger values, it's going to get more vertical, and at infinity, it's going to be exactly vertical. So this is how a slope field looks like for this equation, but again, they are very hard to do with paper and pencil. So what we are going to do is we are going to repeat this slope field, and we are going to sketch the solution, but we are going to use a computer. So recall that the solutions curve have to be tangent to the slope field. We are going to redo this slope field, but much better with a lot of points in between with much more segments. And this is what we get. That is one possibility. It's the same slope field as before. Notice at 0, we get slope 0. At pi over 2, which is more or less over here, we get the slopes 1. Here we got this more or less over here, the slopes negative 1. Nothing changes in this axis, which is the t-axis. Nothing changes in this axis. It changes only on the vertical axis. And for example, at so what do we have here? So let's verify that this slope field is correct. This is the slope field for f of y equals sine of y. Let's verify that this is the right slope field. So okay, we have sine of y. This is our right hand side. So what is the value of the sine function at 2 pi? Well, it's 0. So at 2 pi, which is more or less here, you see, it's hard to see, but here we have 6, and a little bit, so 2 pi, and the function has all the segments are horizontal, which means yes, horizontal segment. So which means that the sine function is the graph of this function is 0 and agrees with the fact that it's a sine function. Then here at 3/2 pi over 2, which is more or less over here, we see that the slopes are pretty close to -1, which is okay because this sine function and the sine function is at -3 pi over 2, should be negative. Then is 0 at pi. We don't see it here because we have values a little bit after pi, a little bit before pi, but we don't have the values on the slope field exactly at pi. But if we had, you see one is negative, the other is positive, so it should be 0. So 0 at pi, and then at pi over 2, this is more or less pi over 2, we have 1, so positive, and then 0 at 0. So yeah, it makes sense, it agrees, so it's probably this is the right slope field for sine of y. Let's do, and now we can plot the solutions if we want to. So for example, let's do the solutions now that we have the slope field in blue. Let's do the solutions in red. For example, the solutions for 2 pi, well, the solution is going to be 0. The solution for t equals 0, obviously the solution 0. The solution for pi is also 0. But the solution here for this initial condition, well, is something like this, and then something like that. They cannot cross the other solution. We are going to see it doesn't cross here. We are going to see later on that this is actually general property. That is kind of a, let's zoom up so we can do it a little bit better. Suppose we have this initial condition, then the solution has to be like this, like this. Yeah, it's kind of hard to do. Cannot cross that, and cannot cross the other solution, obviously. And here the solutions also, here the solution is 0. We have another solution 0 here. We have for here, for this initial condition, the solution looks like that. Here the solution looks like that. And you see, having the slope field gives you a pretty good idea how the solution behaves. And the solution can be continued to the other side. There's no reason not to do it. And we have solutions like this. This solution is 0. The solution here can be continued to the other side, of course. And the solution here should be something like this. The solution here should be something like this. And you can do it for other initial conditions. So having the slope fields give you a qualitative idea of where how are the solutions curves for the differential equation. We haven't solved the differential equation. We are just plotting the right-hand side and sketching qualitative graphs for solution. This has to be solutions. Let's do the same for now the logistic equation. The logistic equation that we solved in a previous video. Okay, we are going to sketch the slope field for the equation, and then we are going to be able to, we know we have graphed these solutions before, so let's see if we can recover those solutions. We need to graph the slope field. If we have a computer, we can do it. This is what we get. Notice I put arrows here, but they should be slopes. No, with arrows here show the direction of increasing time. When we move in that direction, this is the direction of increasing time. So some people, instead of slopes, graph arrows to indicate in which direction the time grows. And we see in this case at 1, we have a pretty nice solution, which is the solution equal constant, equal 1. Not exactly there. There is this gonna be the solution. The solution 0 is right there. And the solution here, what is doing? Well, the solution here has to go more or less. We cannot cross this slope field, so we need to go somewhere here. Notice that we cannot cross, so something like this. And over here, well, similarly, we cannot cross this slope field, so it has to be something like that. And here, well, this is gonna be more difficult, but let's see if we can do it. It has to be something like this, something like this. Cannot cross the other. So this is how the solution looks like. And this is, let's verify that we have the correct slope field, that the computer did a good job. So this is the equation that we want to work with. This here is the function f, which is not function of t, is only function of y. So because of that, nothing should change in the horizontal axis, and this is true. The slope field doesn't change. It's the same slope field as we move in on the t-axis. Nothing changes, no slope changes on the horizontal axis. The slopes are all the same. You see here, the slopes are all the same on the horizontal axis. Okay, what happens for y bigger than 1? For y bigger than 1, this factor here is negative, this factor is positive, so the product is negative. And this is what we get here. For in this region, the slope field is negative. Cool. What happens? So let's say it. Here the slope field should be negative, and it is. At f equal at y equal 1, we should get horizontal slope fields. Let's put it here. And this is what we got. And at y equals 0, also we should have horizontal slope fields, and we got them. And in between 0 and 1, we should get positive. And why? Because between 0 and 1, this factor is positive and this factor is positive. So the result is positive. So positive. So it matches the graph, so we are pretty confident that this is the graph. And this type of calculation, matching the differential equation with a graph, this is basically the homework that you need to do if you want to practice this type of things. This is the homework that we need to do, matching equation with slope fields. One last comment before we move on from slope fields is that the slope field is telling us something, an important property of solutions of differential equations. Solution of differential equation with different initial data or initial conditions do not cross. So we have seen in the previous pictures that we never had a solution that starts here and does something like this, or does something like this. The slope field doesn't allow it. So a picture like that cannot happen when y1 and y2 are solutions of the same differential equation with different initial data. Here are different initial data. The solution cannot cross. And why is that? Because if they cross, then what happens at the crossing point? Well, at the crossing point here, if they cross, this solution has a slope field or a line tangent to the graph of the function with this slope, and the other solution has a tangent line with a different slope. That means, because these two are solutions of the same, these functions are solutions of the same differential equation, that means that y1 satisfies the equation, and also y2 satisfies the same equation, and at the same point, this f has a different value from this f, because for one solution is this slope, for the other solution is this slope. But that cannot happen because f is a function. Because it's a function, f at each point, ty, at each point, it has a unique value, so a unique slope. This cannot happen. Okay, so solution of differential equation with different initial condition can never cross each other. They have to be something like that, for example. Okay. Now let's move on to a second type of graphical analysis of solution of differential equation without computing the actual exact formula for the solution. And this second type of graphical analysis can be done for a particular type of differential equation that they are called autonomous differential equations. So the next graphical analysis we're going to make can be done only on a particular type of differential equation which are called autonomous differential equations. What are these autonomous differential equations? A differential equation of first order is called autonomous if the right-hand side of the equation does not depend explicitly on time. So most of the equations we have been working today and in previous videos are in fact autonomous. So what this condition says is, in word, is that there is no explicit t dependence, independent variable, on the right side of the equation when written in normal form. Okay, so for example, the logistic equation. The logistic equation is autonomous because this is a constant and this is a constant, and the only dependence on time is through the unknown function. So this is autonomous. What else? The linear growth, the exponential or decay equation with linear term. If these are constants, then this is autonomous. What is not an autonomous equation? Well, for example, the logistic equation in the case that the coefficient actually depends on time. So if the growth rate is a function that depends on time, for example, increases when the population increases, then this equation is not autonomous anymore. And the same happens for the immigration term or emigration term. If as time goes, the emigration gets larger and larger, so we have explicit t dependence on the right hand side, then this equation is not autonomous. And the slope fields of autonomous equations, well, we have seen that, for example, the slope field of the sine of y, this is an autonomous equation now. We have the name for that. Recall, it was something like that, and there is no change in the slope field on the t-axis because there is no change here on the t-axis, on the t variable. So all these little slopes are the same on the t-axis because they don't change because there is no t dependence. If the equation has a t dependence, then the slope field changes along y. Look here, we have vertical, then, so for example, vertical, here is 0, here is positive, and here is vertical but positive. Here is vertical negative. So it changes along the horizontal axis. So it's very easy to spot what equation is autonomous and which is not when you look at the slope fields. Okay, hopefully we know what is an autonomous equation now. And for autonomous equations, so for equations like these two and not for these two, we can do a graphical analysis that doesn't require a computer, just paper and pencil. We call it the qualitative solution curves, the sketching of these solution curves, and we are going to show how this is done with an example. And the example is going to be the logistic equation again. We are going to work with the logistic equation. This is the growth rate, this is the carrying capacity. Both constants are positive. And the idea of this analysis is, again, we don't require a computer, just paper and pencil. The idea is that what we are going to do to graph the qualitative solution curves without having the solution formula. We are not going to use the solution formula for the solution, that we already have it, but we are not going to use it. For any solution y of t, we find which intervals of y values where the solutions are increasing or decreasing functions in time. It's complicated, hard to understand, but this is what we are gonna do. We are gonna do it, and then we're gonna read it again, and it's gonna be easier to understand. So, what are we going to do? Solution. We want to graph the solution curves. We're going to graph y of t without computing y of t, without knowing what y of t is, only knowing the right hand side of the equation. So let's write down the equation. Let's go to blue. Y prime we know is r y 1 minus y over k. Recall, we have a formula for the solution, but we are not going to use it at all. So we are going to write the right hand side of the equation as f, let's put it here, as f of y. So that means the equation is y prime is equal f of y. There is no explicit t dependence on the right hand side. Okay, what do we want to do? The first step is we are going to graph. We don't know what the solutions are, so we cannot graph y of t, but we can really graph f of y versus y. That we can, because f of y is just a polynomial in y. So that is perfectly fine. We can graph it. And the first thing we are going to do is 1a is to find the roots or the zeros of f. So find the roots of the polynomial f of y. So what is that? F is equal 0 means that r times y 1 minus y over k is equal 0. R is different from 0, that constant, so that goes away, and that implies that we have two solutions. The first solution is either y is equal 0 or y is equal k. So either this factor is 0 or this factor is 0, which means y is equal k. Alright, so we have the zeros. We know that now what we're going to do is second 1b is rewrite we are going to rewrite f as follows. F of y, so I'm going to multiply here and multiply there, so I'm going to rewrite it as ry minus r over k y squared. Well, we know what that is, isn't it? This is a parabola. So we can put it a little bit down here, and this the other is okay. So what we have here is a parabola that opens downward, isn't it? The parabola is here, and this is a negative coefficient, so it's not a parabola like this, it's a parabola like that. And where are the zeros? Well, the zeros are at 0 and k. So if we have a graph of f with respect to y, the zeros are at 0 and at k, and the parabola has to be the graph has to be a parabola that opens downwards, so it has to go through here and then like this. So I have a better picture right here. So this is the graph of the function f with respect to y. And there are three main regions here determined by the values of f. Here we have the region where f is positive, which is here. These values of y, f is positive. You see, for for these values here, the values of the function are positive. Then we have the region where f is negative, which is here and is here. By that I mean this interval of y's and this interval of y's. The function here, you take a value, you take a value in this region, or well, say here, and the value of the function is negative, and the same here. Okay, so this is an important part. So determine the interval on y where f is positive, well, here, and determine the values of the intervals in y, where f is negative. Did it. Perfect. So now what do we do with that information? Now comes the important part of the analysis. So this is the part 3. Analysis, understanding what all this means. Take any value of the time variable t, for example, t1. Okay, let's grab a time t. Evaluate a solution of the differential equation. Suppose we have a solution y of t. Evaluate that solution at that value t1. Okay, you're gonna get a number, isn't it? That solution at the time t1 is gonna give you a number. Okay, that number has to be in this axis, because this is the values, this is the axis of the value of the values of this all possible solutions. So this number here has to be in this axis. Okay, so suppose that this value, we have chosen a t1 such that the y value is in a region where f is positive. Let's say, for example, it could be here, or it could be here, I don't know, but let's suppose it's in this region. Okay, I have a picture for that. Suppose that value of y1 is here. This is in the region of f positive. Okay, so what? Well, if that value is right there, then what happens with so recall this value is the value of a solution at t1. So the derivative of that solution, the time derivative of this solution at that time t1, because this solution of the differential equation has to be, that value has to be f at the solution at t1, because it's solution of the differential equation. But this is f at y1. And recall, we are considering the case that y1 is such that f is positive, is right there. Well, what we have concluded from here is that for that solution, the derivative at t1 is positive. This is the derivative, and it's positive. Okay, so that solution then that solution, because has derivative positive at t1, so the actual solution, not the derivative, just the solution, is an increasing function in time, because it has derivative positive. Okay, then what happens if we have another time t2 that is bigger than t1, but close enough, close to t1 but bigger? Oh, I forgot something. Close enough. There. What happens? Well, the value of that function if y2 is that value, because the function is increasing, the y at t2 has to be bigger than y at t1, which is y1. So if we want to graph this number, the function evaluated at a later time, later than t1, then this number is gonna be bigger than the number y1. So we are gonna be, it cannot be here. It has to be on this side. It has to be there. I don't know where, but to the right. So here. And the same is going to happen with any y1 in this region. If you pick up a y1 here, a y2, it has to be here. If you pick a y1 here, a y2 has to be here. You pick a y1 here, the y2 has to be here. So values of the function in this interval, they are moving always to the right because f is positive. That is the conclusion of this part. Now let's repeat the same analysis, but now suppose that this time t1 that we chose is such that the value of the function at that t1 is not in this region. It's either here or here, suppose, because it has to be in this line. It's either on this segment or is in any of these two segments. Now let's consider that case. Suppose y1 is such that it's in a region where f is negative. So I draw it here, for example. F is negative in that region. Well, we do the whole analysis one more time. Then, what happens? Recall, we are evaluating a solution. So what happens with the derivative of that solution at that time t1? Well, because it's a solution, has to be the values of f evaluated at that y of t1, which is f at y1. But we are assuming that we are in the value of y1 is such that this is negative, which means that the solution evaluated at that value of t1 is a solution with negative derivative. And that means that y of t at that time t1 is a decreasing function in time. You see, only we are understanding what the equation means. And then for any t2 bigger than t1, but close enough, what is going to happen? The first thing is going to happen is that we need more space. There. Or no, let's put it here. And let's move this thing a little bit higher up. There. What is going to happen then? Well, if the function y at t2, that value we call it y2, we know because it's decreasing that has to be smaller than the value of the function at t1, which we call y1. So the next value, it has to be smaller, so it has to be to the left now. If we chose this y1, y2, it has to be less. It has to be here. So I have a nice picture for that here. So the values of the function now, they go in the opposite direction, because grab any y1, the y2 at the later time has to move to the left. And here the same. This is y1, y2 has to move to the left, y2. So the values of the solutions in this interval are decreasing because f is negative, and also decreasing here because f is negative. So what we have as conclusion is that picture here. The sign of the right hand side of the equation says that implies that the solution values on this region has to decrease, in this region has to increase, and in this region has to decrease. Now we can, this is the direction of increasing time for the solution. Let's put that time into the graph. So what we are going to do is we are going to get rid of this axis. We don't need it anymore. We only need the horizontal axis. We are going to put it as a vertical axis. And now we are going to put here time. And the information we have here, we are going to keep it. So we have 0, we have k, we have here decreasing solutions, we have here increasing solutions, we have here decreasing solutions. That means if you start with an initial, these are the equilibrium solutions, 0 and k. If you start with an initial data here, the solution has to decrease. It can never cross the constant solution. If we start with the solution here, it has to increase. It can never cross the equilibrium solution. If we start here, the solution can never cross. If we start here, the solution has to go like this. And this is how the solution looks like, just by studying the right hand side of the equation. So this is what we are going to do. We are going to put the horizontal axis as vertical axis. We copy the information, we put the new axis, and then they graph the constant solutions, and then we graph all the other solutions. We do that, and this is what we get. The solutions here, y equal k, y equal 0, recall they are called equilibrium solutions. And now that we have all the other solutions nearby, and the solutions bunch up around k, and they go away from the solution 0, we say that the solution k is stable equilibrium, the solution 0 is unstable equilibrium, and we have used, to construct this graph, we have used, of course, the information from the slope fields that say solutions do not cross. And here they cannot touch either, because suppose a solution touches here, then what is going to do? It has to increase, but it cannot, if it touches and increases, has to cross, but that cannot happen. So the solution cannot touch. If we have a constant solution, this solution gets closer and closer and closer, but it never touches, and it's always increasing. This is the graphical analysis. We did an example with the logistic equation, but for any autonomous equation, you repeat the same steps, and you are going to end up with a pretty nice graph of qualitative solution curves without having the formula for the solutions. At no point in this analysis we use that the solution curve are actually given by this formula. Here I think is y0 minus k, or could be the opposite, exponential negative RT. We never use the solution at all. We only use that f of y is ry1 minus y over k. That's all we use. With that information, we get this, and paper and pencil. So this is a good place to stop. See you guys in the next video.